As we saw in previous videos, we can use a quadratic equation. We can play around with different parameters of a, b, and c to vary the shape of the quadratic equation. So we can use it to fit different curves in real life. Now, it might not perfectly fit the entire curve, but if you want to give a general idea of the shape of the curve, you can use quadratic equation to describe or design objects. We're going to look at an example problem where we're designing an enclosure using quadratic equation. You can think about what other curved physical objects that you've seen on a day-to-day basis. Maybe a bowl, or maybe the end of a airplane, the nose of the airplane, or a rocket. So a lot of different things have some kind of curvature that you can closely fit with a quadratic equation. So that's what we're going to look at in this example. In this example problem, we're going to take a look at designing a tent that we're describing as having a quadratic equation front surface, or described by a quadratic equation, and enclosing a table. We're going to start by defining the requirements of this tent, and then try to answer two questions. Then we're going to set up the problem, thinking about it from a physical perspective, then looking at purely solving the math components of it, and then going back and looking at the physical components. We're not going to worry about the length of the tent. We're just going to assume that the shape of this quadratic equation is propagated through the tent. So we're just really looking at this from a 2D perspective. So the first requirement of this tent is that the width must be between 12 and 20 feet. And so we're defining the width of this as this base component right here. So this is the width of the tent. And we're defining it as having a max width, because if it's wider than that, it's taking up too much floor space, and 12 feet wide as the minimum, because anything narrower than that, now you're actually going to be on a section that has concrete, right? So you can't put in the stakes. So that's why we're saying that 12 to 20 feet width is a requirement for this tent. We're told the dimensions of the table: 6 feet by 6 feet by 3 feet. And one of the requirements is that the edge of the table needs to be touching the tent. So that helps us define design requirements for the quadratic equation. So that's referencing these points right here. So this is my quadratic equation that we're going to try to describe. Now, even with this range of widths that the tent must be kept at, and the contact points of this tabletop, there are still an infinite amount of solutions that can be found, all within a range, right? And so what we're going to do is try to identify what these ranges look like, and then graph them. And then there are two questions that we're trying to solve: what are the smallest and largest peak tent height? And we're defining peak tent height as the height from the top of this tent to the floor. All right, and the problem setup. So the first thing we need to do is define the origin, the location of origin. And that's really important because we need that to define these requirements in terms of points. So here we define our origin. We set it up so that x equals 0 is right underneath that peak tent location. That gives us the ability to take advantage of the symmetry of this problem. Whenever we can find symmetry in either the horizontal or vertical directions, usually you want to put an axis there, because then you can simplify things a lot, and we'll see that show up here. We're going to define y as 0 at the floor and positive in the vertical upwards direction. That's a pretty conventional method of defining y values. So with that, we can see that 3, 3 and negative 3, 3 are the 2 points where the tents are going to be touching the quadratic equation tent, or the table will be touching the tent. So that's nice, and we know that because the table is 3 feet tall and the table is 6 feet wide. So if it's 6 feet wide and we split it down the center, then it's going to be plus 3 on one side, negative 3 on the other side. So that's how we define those points. We're going to do the same thing for the width range. Negative 10, 6 and 6, 10 are going to be our intercept points for x-axis. We know that because our x-axis is down here where y equals 0, so it's at the floor. So that's going to be the range. So it's going to be negative 10, 6 to negative 6 on one side and 6 and to 10 on the other side. So we'll see how we deal with ranges in a second. Here we show it on a 2D graph, right? So there's my negative 3, 3, my 3, 3 points for the where the tent touches the table. And then in this range right here, negative 10 and negative 6 on the x-axis are my left side intercept range, and 6 to 10 are my right side x-intercept range as well. So we start by looking at the quadratic equation. We make sure that origin is set. It's set here and set in the graph here. So we're all good there. We recognize that there is symmetry. So I know that the peak point is on the y-axis. So I can, like we solved in a previous video where we have max and mins on the axis, we set dy dx equals 0 at that y-axis, or at x equals 0. dy dx in general form is 2x plus b. If we plug in dy dx is equal to 0 and plug in x is equal to 0, so that's on the y-axis, we see that b is equal to 0. So we already removed one of the terms in my quadratic equation just by recognizing their symmetry. Now you could define the coordinate system any way you like. You can move it. If you did move it, your quadratic equation will be slightly different, just like we've seen in one of the most recent videos, where we can shift the quadratic equation left, right, and in the vertical direction. But there's no reason to do that, right? So we want the simplest form of this quadratic equation, because all we care about is the shape, honestly. So the simplified form of this quadratic equation, where now b is equal to 0, is now just y equals ax squared plus c. We look at this equation and think on the physical perspective, what do c and a need to be? C, we know, is the variable height. And we know that because if we set x equals 0, then we know that y equals 0 because it's right on the y-axis. Or sorry, y is equal to c because it's right on the y-axis. So whatever c is will become my peak tent height. So that's useful to know. And I know that because of the way I define my y coordinate system, that's going to be a positive value. I also know that a is going to be negative because we have, if you just look at this quadratic graph right here, the edge of this tent, that's a maximum. That's demonstrated with a maximum peak tent height. And we know from previous videos that a is negative when we have a peak, when we have a max. And a is positive when we have a minimum, right? So like a negative x squared, y equals negative x squared, we have a maximum point. When we have y equals positive x squared, we have a minimum point, right? So those things are going to be useful as we evaluate whether or not our final solutions make sense. All right, so now we can start looking at requirements. One of our requirements is that it needs to go through the 3, 3 point. That's what we looked at earlier here, right? So that it's touching the table edge. The tent is touching the table edge. So we can literally just plug in 3, 3 into this simplified quadratic equation. Now I don't need to also include the left side table edge, negative 3, 3. I don't need to do that because I already have the symmetry accounted for with b equals 0. So once I set this up for one of the points, I'm already automatically setting up for the other point. So I plug in 3, 3. I get 3 is equal to ax squared, or 3 squared, plus c. So now I have a relationship between a and c. So I say c is equal to 3 minus 9a, and I know that a is going to be negative and c is going to be positive. We discussed that earlier. If I use negative 3 and 3, I would have found the same thing because it's negative 3 squared a plus c as well. So it's going to come out to the same relationship, which is what we expect. Now I know that my other requirement is that we're going to range between 12 and 20 feet wide for the base of the tent. So I know that that's going to be interpreted as between 6 and 10 on the positive side, and between negative 10 and negative 6 on the negative or the left side of the axes. Again, we don't need to do it for both because we set b equals 0, so we have symmetry already pre-built into this equation. Okay, so what we could do is solve for the generic form and relate a and c. That's not what we're asked to do. All we're asked to do is find the limits. So I know that I can use 6, and then I can use 10, and one of those is going to be the answer to the peak tent that's the largest, and one that's going to be the smallest. Before we continue and solve this problem, can you intuitively think about which one is going to be the largest and which one's going to be the smallest? Think about what you know about quadratic equations and how we modify them. All right, so let's take a look. If you're not sure, that's okay. We're going to walk through this and then graph them. So the first one we're going to look at is the limits at negative and positive 10. So I'm going to use 10, 0 as my point. So if I plug that in to y equals ax squared plus c, I get y is equal to 0 is equal to ax squared, or a10 squared, plus c. So that 0 is equal to 10 squared is 100, 100a plus c, which we defined earlier in relation to a, so 3 minus 9a. So I plug that in here. So we solve for it, then we can see that a is equal to negative 3 over 91. Not a pretty number, but we know our final solution. So we're going to keep it in fractional form here. All right, so I have a, I have b, now I need c. But I have this relationship with a and c, so I can just plug it in. So I plug in negative 3 over 91 up into this equation. And so I get c is equal to 300 over 91. Okay, so now I have a, b, and c. I can plug them into the quadratic equation form and see my equation. Negative 3 over 91x squared plus 300 over 91. If I graph this, this is what we get. Right? So this is my peak tent height for this intercept location. So that's one of my limits. We're going to do the same exact thing with a intercept at x is equal to 6, or x equals plus or minus 6. So we plug in 6, 0 into the quadratic equation, and we solve for a by substituting the c equation 3 minus 9a down here. And we see that a is equal to negative 1 over 9. We'll plug that back into the c equation here and solve for c, which is 4. And when we graph it, when we graph y equals negative 1, 9 x squared plus 4, this is the shape we get. Did you expect the point of intercept at plus or minus 6 to have a higher y-intercept point? Hopefully you did, right? So I think it intuitively makes sense. You're basically squeezing, so if you're gonna pull up to squeeze, and this is consistent with what we looked at when we changed the a value, and that's essentially what we have to make this one narrower in order to hit these 2 points here. All right, so now we have our smallest peak tent height. That's once we contact our max width of the tent, the negative plus or minus 10, or the 20 feet wide case, and that came out to be 3.3 feet, right? That's the 300 over 91 term here, the c term here. The largest peak tent height would then be this one right here, right? 4 feet. And that's the case where we intersect the x-axis at negative 6 and positive 6, right? So this case is the 12-foot wide tent. If we graph the intermediate points, right? So I graphed it at -6, or at 6. I can graph at 7, 8, 9 as well. We can see the gradient as expected. The further we go from 6 through 10, the smaller that peak tent height would be. So what I want you to do now is hit pause. I'm going to show you the equations for these three values. Do the same thing that we did for the intercepts at 6 and 10, and see if you can get the same equations that I do, right? In fact, if you want to, start this all over at the beginning and then see if you can solve these steps on your own. So hit pause, try it out, and then I'll show you the equations that I got for these three intermediate intercept points. All right, now I'm going to show it. These are all 5 graphs, or sorry, 5 equations that show these intercept points. So this is a very common way of looking at design problems. You have range requirements, and then you have specific requirements. This is a pretty close-ended problem, meaning that there are final solutions for the specific question we're asking. A lot of times there are not. A lot of times you have to, as engineers, design your specific problem so that you close the scope of it and you can actually solve it. But this is an example of what we can use quadratic equations and this concept of max and min and x-intercept points to help us solve simple design problems like this one.